In this video, we're going to look at the equations of lines in 3-space. In 2-space, you can have vector equations, parametric equations, and scalar equations. But in 3-space, you can only have vector equations and parametric equations. Scalar equations do not exist in 3-space. So we're going to find the vector and parametric equations for the line containing these 2 points. So what I'm going to do is I'm going to form a vector between point 1 and point 2. And if I want to do that, if I want to form a vector between point 1 and point 2, I'm going to take, remember, the position vector from the origin to point 2 minus the position vector from the origin to point 1. And you can subtract those 2 points, those two position vectors, and you'll get the vector between point 1 and point 2. So we go ahead and we do that. So we have 2 minus minus 4. Okay, so 2 minus minus 4, right? Negative 3 minus 1, and then 5 minus 3. So therefore, the vector p1, p2 is equal to 6 minus 4 and 2. Okay, what we're going to do is we can see that this vector right here can be reduced. And so we're going to reduce that to use that as the direction vector. These two vectors right here, they have the same direction. The only difference between these two vectors is their magnitude. And all we really want is we just want the direction, right? The magnitude is inconsequential. So the vector equation for the line OP is going to be negative 4, 1, 3. So a point on the line plus the parameter t, and then 3, negative 2, and 1. Okay? And then if we want to find the parametric equations, so as you can see right here, we've got the same vector equation. So if we want to find the parametric equations, we just say x is equal to negative 4 plus 3t, y is equal to 1 minus 2t, and z is equal to 3 plus t. And one thing to consider is that if you want to find, say, for example, an x-intercept, we'll actually write this out over here. If we want to find the x-intercept, then y is equal to 0, but also z is equal to 0. So we find the t value that makes both y and z equal to 0 simultaneously. Okay, and it may not exist. But that's how you go about finding the various intercepts with the axes. What's new here is symmetric equations. So for this new form, we can isolate t in each of the parametric equations and then eliminate t. So still working with the same example. So what I'm going to do here is I'm going to isolate t in each of these parametric equations. So I'm going to bring everything over to one side so that t is by itself. So if we look at this first one right here, that would be x plus 4 all over 3 is equal to t. Okay. Alternatively, if I brought everything over to one side, I would have y minus 1 all over negative 2 is equal to t. And then I would have z minus 3, and then there's no coefficient in front of t here, so I could say like divided by 1, for example. And that's also equal to t. So since all of these 3 equations are equal to t, I can make my symmetric equations. I can say that x plus 4 over 3 is equal to y minus 1 over negative 2 and z minus 3, and I'll say over 1 right there. They're all equal. Okay. Now you might be wondering, okay, well, why have I left a negative in this denominator here, and why am I even bothering putting the 1 right here? Well, we're going to see this in a second, okay? So note that the numerators are the opposites of the known point, so opposite sign of the known point. So if I look at my known point, negative 4, 1, 3, and then over here, positive 4, negative 1, and negative 3. So you can see that the numerators right here, these constants right here, 4, -1, and -3 have the opposite sign as the known point used in the vector equation. And the denominators, and this will answer your question as to why I've left the negative here and why I put a 1 here. The denominators are the components of the direction vector used, and in this case it was 3, -2, and 1. Right, so if we look at the direction vector 3, -2, 1, those are my denominators. So for a line with the direction vector component d1, d2, d3 containing point x0, y0, z0, the symmetric equations are as follows: x minus x0 all over the x component, y minus y0 all over the y component, and z minus z0 all over the z component right there. Okay? So these are your symmetric equations. These are the components of the direction vector, and these right here have the opposite signs as the original point. Okay, so for the line, x plus 4 over 3 is equal to y minus 1 over -2 and z minus 3 over 1. Find the point on the line whose coordinates add to 10. Well, if the coordinates add to 10, then I can make a quick statement right here. I can say, therefore, x plus y plus z is equal to 10. I also have all my symmetric equations right here, and I can turn those into parametric equations. So x plus 4 over 3 is equal to t, so then x is equal to -4 plus 3t. Y minus 1 over -2 is equal to t, so therefore y is equal to 1 minus 2t. And then z minus 3 over 1 is equal to t, so z is equal to 3 plus t. So here are my parametric equations, which I derived from my symmetric equations. And I also have this further stipulation that x plus y plus z must be equal to 10. So what I can say right here is I can take these two sets right here, and I can say, therefore, x, which is -4 plus 3t, plus y, 1 minus 2t, plus z, 3 plus t, must all equal to 10. Okay, simplifying, I get 2t is equal to 10 and t is equal to 5. So t is the parameter value that would make x plus y plus z equal to 10. So now that I know that t is equal to 5, I can say, all right, sub t is equal to 5. And I can say x is equal to -4 plus 3 times 5. So then x is equal to 11. Y is equal to 1 minus 2 times 5, which is equal to -9. And z is equal to 3 plus 5, which is equal to 8. So therefore, my point is going to be 11, -9, and 8. We can check that out by adding these three coordinates together and seeing if they do in fact equal to 10, and you can see by inspection that they do. Find the point where the previous line intersects the xy plane. Well, if it's intersecting the xy plane, that means that z has to be equal to 0. So I'm just going to quickly write right here that, therefore, z has to be equal to 0. Okay, so if z is equal to 0, then I'm going to take my parametric equation for z. Z is equal to 3 plus t. 0 is equal to 3 plus t, and t is therefore equal to -3. Well, if t is equal to -3, then what I'm going to do is I'm going to take t is equal to -3, and I'm going to sub t is equal to -3 in my parametric equations for x and y. So x is equal to -4 plus 3 times -3. So x is equal to -13. Y is equal to 1 minus 2 times -3. So y is equal to 7. And I'll say, therefore, -13, 7, and 0 is the point where the line intersects the xy plane. In this last example on the page, it says find if possible the point of intersection of the lines. So I've got this line right here, which is OP is 1, 2, negative 3 plus 2, negative 2, 4, 1. And then 2 is x plus 2 over 2, y minus 3 over negative 2, and z minus 4 over 3. So looking at this right here, by inspection, I can come up with the direction vectors of the two lines. So the direction vector of this line right here is given to me quite clearly as negative 2, 4, and 1. If I look at this right here, these are the symmetric equations, but you'll recall that the denominators of the symmetric equations are, in fact, the components of the direction vector. So this right here is 2, negative 2, and 3. Okay, so the first thing that I'm going to do is I'm going to see if these lines are parallel. Right? Because if they're parallel, then I know they won't intersect. So that should be your first check. Just look to see if the lines are parallel, because if they're parallel, there's no point in doing any more work. They will not intersect, right? Or potentially they could intersect infinitely if their lines are parallel and what we call coincident. And what we mean by that is if they're parallel and coincident, then the lines just sit on top of each other, and then they've got infinite points of intersection. Okay, but you don't want to waste your time with that. So what we're going to do is we're going to say check if line 1 is parallel to line 2. And we do that by checking to see if d1 is equal to some scalar value times d2. Okay, so this is how we're going to check to see if the two lines are parallel. Well, let's look at the direction vectors. D1 is negative 2, 4, 1, and D2 is 2, negative 2, 3. So you need to look at this and just say, is there any scalar value that would allow D1 to equal to k D2? And you can probably see that there isn't. So you can say, therefore, by inspection, no k value exists. So therefore, line 1 does not or is not parallel to line 2. Okay, so that's kind of the notation that we might want to use here just to show that we're checking to see if the lines are parallel. We can see that they're not based on the direction vectors, and so we say line 1 is not parallel to line 2. Okay, so what I'm going to do is I'm going to create a set of parametric equations for each of my lines. So for line 1, my parametric equation would be x is equal to 1 minus 2t for x, and for y it's going to be 2 plus 4t, and z is going to be equal to negative 3 plus t. For line 2, it's going to be x is equal to negative 2 plus 2s. I'm going to use different parameters for my lines because they're separate. Y is equal to 3 minus 2s, and z is equal to 4 plus 3s. Okay, so if these lines intersect, that means that their x, y, and z have to be the same. So what I'll do right here is I'll set x and y equal to each other. Okay, so let me set x and y equal to each other. So right here, that means I'm going to have 1 minus 2t is equal to negative 2 plus 2s. And then I'll have 2 plus 4t is equal to 3 minus 2s. Well, this works out really well. I need no further manipulation because if I add these two equations, I can eliminate the s variable. Adding these two equations yields the following. Well, 1 plus 2 is 3, and then negative 2t plus 4t is equal to 2t. And this right here, negative 2 plus 3 is equal to 1. So 2t is equal to 1 minus 3, and t is equal to negative 1. Well, if t is equal to negative 1, then what I can do right here is I can sub that into, let's sub it back into the first equation. 1 minus 2 times negative 1 is equal to negative 2 plus 2s, and s is equal to 5 over 2 if we isolate for s. Okay, so I have now found t and s that makes x and y equal to each other, which they should be if the lines intersect. Now let's check to see if this works. Okay, I'm going to find the z value. Okay, so then let's set the z value equal to each other. Okay, so let's put a line over here. Okay, and a line over here. And I'll say check z value. So -3 plus t is equal to 4 plus 3s, and I'm going to sub t is equal to -1 and s is equal to 5 over 2. So let's see if these parameters allow the z value to be equal to each other. If that's the case, then the lines have a point of intersection. All right. If it's not, then they won't intersect. So -3 plus -1 is equal to 4 plus 3, 5 over 2. All right, and I'm going to clean this up, and I'll say -4 is equal to 23 over 2. We know that's not possible, okay? So I'll say, therefore, although x and y are the same, right? We found two parameters that allowed x and y to be the same. The z value is distinct in each line. Therefore, line 1 does not intersect line 2, and you say line 1 and line 2 are skew. And that means that in 3 space, line 1 and line 2 are not parallel, but they also don't intersect. Okay, and so what we'll do is we'll throw a box around that answer. So it says, note on example 3, a direction vector for line 2 is 2, -2, 3. Note that this is not a scalar multiple of the direction vector for line 1. Well, yeah, we said that already. We said that by inspection, line 1 is not parallel to line 2. And so these are not parallel lines, and they don't intersect, so they are called skew lines. Okay, there are 3 possibilities for lines in R2. You can have coincident lines. So coincident lines means that they are have infinite solutions, and I think I already mentioned this already. So this is your line 1, okay, and then your line 2 literally sits right on top of it, okay. So let me just move this over. Okay, line 1 and line 2. Okay, so they are parallel and coincident, which means that they have infinite points of intersection. You can also have parallel and distinct. So right there, parallel and distinct is the following. A line there. I'm just copying and pasting these lines. Here we go. Okay, 0 solutions, they will never intersect. And then you can have intersecting lines in 2 space where you have this right here, and then you have another one right here with 1 solution, your point of intersection. In 3 space, we have a bit of a different set of different possibilities, right? So you can have 2 lines that intersect in 3 space, okay? So like they intersect at a point. You can have parallel and coincident lines, again, so this is your line 1, and then your line 2 is right on top of the other one, right? So this is, I'll actually write line 1 and line 2 are on top of each other, okay? You can have parallel and distinct, just as we had before. Okay. All right, there's your parallel and distinct, 0 solutions. And then you can have skew, okay? And so skew is where the lines are, they're headed in different directions, but they are spaced out in 3 space that they will never intersect. And it's a bit hard to picture on a 2D page, but you could basically like hold your arms, one forearm on top of another forearm, point your forearms in different directions, and then separate them. And if that's the case, then you'll see that, okay, your forearms can have different directions, but they might never intersect in 3 space, right? So in this case right here, D1 is not parallel to D2. It's not a scalar multiple of D2. So that means therefore line 1 is not parallel to line 2. No point of intersection. So they are skew. Okay? You'll note over here that I have some notes on what parallel and coincident mean. I also have some notes on what parallel and distinct mean. Okay, let's move on to this question right here. Classify the pairs of lines as coincident, parallel, distinct, skew, or intersecting at a point. And there's a kind of like a helpful tip here. Check the direction vectors first to see if they are scalar multiples of each other, in which case they are parallel, and then you have to decide, are the lines parallel and coincident? Okay, do they have the same direction vector, and then will they have the same points as well? Or are they parallel and distinct, which is that they have, you know, like a multiple of the scalar of the direction vector, but they will not have the same points. So you just test a point from one line and show that it does not exist on the other. Okay, so let's check this right here. So what I'm going to do, the first thing I'm going to check is if the lines are parallel. Well, I have my direction vector here. That's easy enough to get for line 1, -10, -6, and 8. Now, this one is a little bit trickier because you have this format for your z component. So x minus 4 over 5 is equal to y plus z over 3. And then what I'm going to do here is I'm going to factor out a negative from the numerator, and I'm going to say z minus 1 all over 4. And then I'm going to have this right here. I'm going to bring that negative to the denominator, and I'll have z minus 1 over -4. And then we have, therefore, my direction vector for 2. The components are, again, just the denominators, 5, 3, and -4. So what I'm going to do is I'm going to check if parallel. Okay, so I'm going to take D1 right here, which is -10, -6, 8, and see if there's some scalar factor that can make these two equal. And so you can see that k would be equal to -2. So if k is equal to -2, there is a scalar factor that makes these two equal. And so we say, therefore, line 1 is parallel to line 2. Okay, so if line 1 is parallel to line 1, we can say check if 1, 4, 5 from line 1 exists on line 2. So I'm just taking this point right here and checking to see if it exists on line 2. So I'm going to sub it into the symmetric equations. So 1 minus 4 over 5 is equal to 4 plus 2 over 3, which is equal to negative bracket 5 minus 1 all over 4. And what I get right here is -3 over 5 equals to 2, which is equal to -1. Well, we know that that's not the case. Okay, and so therefore they are in fact parallel, but they do not share any points, right? So if we think about this right here, like they have a multiple of the direction vectors, but they do not have the same points, right? So what we have right here is they do not have the same points. You can test a point from one line and show that it does not exist on the other. Well, that's what we just did. We took a point from this line right here and we subbed it into the symmetric equations to see if that point also exists on the second line. We see that it doesn't, so therefore we say, we'll say therefore line 1 and line 2 are parallel and distinct. Okay, moving on to the final example right here. We've got these two lines and we're going to check to see if they intersect. Okay. So the first thing that we're going to do is we're going to look at D1 and D2. Well, D1 is 1, -1, 1, and D2 is -2, -1, and 2. So we'll say by inspection, D1 is not equal to KD2, and therefore line 1 is not parallel to line 2. Okay, so if it's not parallel, that means that either they intersect at a point or they are skew. So I'll create my parametric equations for each. So x is equal to 3 plus t, y is equal to 2 minus t, and z is equal to 1 plus t over here. So that's line 1. This is line 2. Line 2 is x is equal to -2s, y is equal to 1 minus s, and z is equal to -2 plus 2s, right there. So I'll take these two equations right here, and I'm going to set the x and y equal to each other, because if they intersect, then those 2 points, those two values should be equal. Okay, so what I'll say is therefore 3 plus t is equal to, and then there's no constant value here, so I'll just say 0 minus 2s. And then over here, I'll say 2 minus t is equal to 1 minus s. And now I can add these equations. So then I get 5 is equal to 1 minus 3s. Okay, and then I get 4 is equal to -3s, and -4 over 3 is equal to s. So I have my s value right there, and I'll sub that in to an equation, and I can maybe sub it into the second equation right here. So 2 minus t is equal to 1 minus -4 over 3. So 2 minus t is equal to 7 over 3, and we'll say t is equal to -1 over 3. Okay, so I have an s and a t value. So finally, I'll take my s and my t, and I'll sub s is equal to -4 over 3, and t is equal to -1 over 3. And I'll check to see if that makes my z value equal. And if it doesn't make my z values equal, then that means that the lines intersect at a point. But if my z values do not equal, then they are in fact skew lines, as we saw before. So 1 plus t is equal to -2 plus 2s. And then 1 plus -1 over 3 is equal to -2 plus 2, -4 over 3. And then 2 over 3 does not equal to -14 over 3. So we can see that these parameters, which make the x and y equal, create distinct values of z. And so therefore the lines are skew. So therefore line 1 and line 2 are skew. Okay, so summary, this is your equations of lines, and these are your tips for equations of lines. You can take a look through them. Okay, thanks for watching.